All right. Well, a lot of my work is in philosophy of science, but I have many interests within the philosophical landscape. So, so in thinking about science, of course, science is such a big part of our lives. We live in a technological society, in a scientific society. Often we make decisions about what we're going to eat, how much we're going to exercise, how we're going to structure our days on the basis of scientific and technological developments. So part of the work I do is to think carefully about when we do have evidence to make the claims that we want to make, or scientists want to make, about a variety of issues. I, by and large, I'm an empiricist. What that means is I take very seriously information about the empirical world that we can get. But also, as I think good empiricists are, we tend to be very skeptical about under what conditions you don't want to say more than the evidence actually allows you to. So some of the work I do is a reflection about images in science, right? There are whole areas of scientific research in which images play a crucial role, right? So if you open up, for example, a journal in chemistry, there's virtually no article there that doesn't have some image or other to present the result of an experiment, a micrograph, at least things like a diagram, and they play a crucial role in the inferences and in the way in which scientists are going to draw results and make suggestions out of the information they gather. So some of the work I do is to think carefully about those images, right? How do they get into the scientific discourse? Which function they play, under what conditions they can be trusted, when they can be very misleading. So we are, of course, in many ways visual creatures. We want to see as a way of knowing things. So one of the big hopes with the development of microscopy was, well, we'll be able to see things that we are unable to given the limitations of our eyes. So much of the work I do is reflect carefully about the images produced by microscopes. And those images are surprising often in ways that they present to us information about things that often we couldn't even imagine. In many cases, for example, when the first electron microscope was applied in biology, not the first, but eventually in the sort of 1940s and 50s, when microscopes were introduced and start being used. For example, George Baladi, who was a microscopist at Rockefeller Institute, he noticed these interesting little dots on the surface near the membranes in a cell. And no one has ever seen things like that before. We cannot see that with an optical microscope, right? The electron microscope gives you far more resolution and you can see much better. So he was puzzled. So, well, literally, he did not know what he was seeing, right? And he said, well, maybe this is just an artifact, right? So he thought, well, maybe we can rule these things out by changing the method of preparation. So he did that, and the little dots were there. Okay, well, maybe if we change the part of the body from which the cells are being collected, or if we change the animals from which we're gathering those cells, maybe there will be some changes. He did those changes, and the little dots were still there. So he said, okay, looks like this may not be an artifact then of of the instrument or the method of preparation. So if it's a genuine new feature of the cell, is there a way of triangulating? Is there a way of using some other instrument that would allow us to gather some additional information about those little particles? So he did. He used an ultracentrifuge the contents of those cells, and he noted that there was a difference in the sedimentation time, which was compatible with the measured size of those little particles that he could measure using his electron microscope. So he said, okay, so it looks like this thing is for real. So he then published a paper in 1955, which gave the least committal title possible, right? The paper was called Small Particulate Component of the Cytoplasm, because that's what it was, small particles, right? He, in the beginning of the paper, he speculated, saying that, well, maybe those particles are mostly made out of acid, given the color in the preparation, using the preparation method, but additional chemical analysis needed. So a couple of years later, that analysis was indeed implemented, and it was mostly ribonucleic acid. So now those little dots are called ribosomes. So this is a beautiful case where literally the biologists there stumble into something because there was an instrument, then there was an image that the instrument created. And he, in that case Pallade, was in many ways in a situation quite similar to the old naturalists that would take themselves, say in the 18th century, get yourself into a ship and go to an unknown part of the world to just record all these bizarre looking creatures that no one had any idea that they were there. And in that way expand our knowledge and our understanding of what was around us. So instruments now in contemporary science are doing something similar that those ships were doing back 300 years ago. They're allowing us to explore domains that were completely inaccessible to us. But they don't always work, right? And of course, as all of us who deal with technology in one way or another know that technology fails, right? And you need to be very careful not to overstep the boundaries of the applicability, of the suitable applicability of those instruments, right? So if you're not careful about how you're using those instruments, you may actually get very misleading conclusions. So some of the work I do is trying to understand under what conditions it's okay to use those instruments, under what conditions we be very careful, right? And of course, that's a sort of, by and large, a case-by-case basis, because different instruments behave differently, right? They have their own kinds of processes and procedures, and you need to know very well how the instrument is built first, so you can know what kind of information it can, in principle, provide about the sample and the study, and what kind of inference you can draw from the images that the instrument produces, right? Now, I mentioned an example of the small, right? So little ribosomes. We have, of course, incredible examples of the very large. And so if you think about the Hubble telescope, right, that gave those amazingly beautiful, intriguing images of all kinds of celestial objects. And it's very tempting for us to look at those images that we can find now in sort of books and coffee table books, and it's very tempting for us to think, oh, if I got myself into a rocket and go to outer space, is that where we're going to see it, right? Well, the answer is, well, yes, if your eyes are about 2 meters large and you keep staring at the object for 2 weeks, right? Because those images are the result of a complex process of composition, right? We have signals, little bits and pieces of light, and they're composed out of a very careful process. So you need to be very careful how to interpret those images. Of course, scientists know what they're doing, right? They're not going to be misled by what the image presents if they're careful about how the instrument was built. But a general public may not know, may not have that kind of background. And the general public may look at those scientific images in exactly the same way we look at a photograph, and use the same convention codes that we use when we look at a picture of grandma, and use at a picture of a Hubble. If you do that, you're bound to make some serious mistakes in terms of what you're going to infer, right? So same thing happens now if you go back to the very small. So often we have microscopes, scanning tunneling microscopes that give information about surfaces of, say, carbon at the nanoscale. Now the nanoscale is sort of 10 to the minus up to 10 to the minus 9 meter scale, right? So you're talking, so for you to have a sense of how small this is, if you think about DNA, right? The distance between the two strands of the DNA, it's about 2 nanometers, right? So that's really, really small, right? So, but we can visualize these things with appropriate microscopes. And some of them actually are very fancy. You look at those images, they're full of colors, right? Of course, there's no color at the nanoscale, because the visible light, things that for our eyes will process as something that has color, it's much smaller. Then it's much larger than what is in the nanoscale. So literally speaking, in the nanoscale, there are no colors. So any image of a nanoscale object that is colored, you know that that color is artificial, right? So again, scientists would know, right? So that means that the color in those images means something very different than they mean when we're looking at a color photograph. So the meaning of color has changed when you look at a scientific image produced at the nanoscale. It doesn't mean the way we would respond to say, oh, that means that the object would look that way, right? Not quite, right? Similarly, of course, being a philosopher, you love to do a little bit of thought experiments, right? So you think, okay, what if I could shrink myself to the size of an electron? And just wandering around the surface of a carbon, right? So what would I see? Would I see what those images from, say, a scanning tunneling microscope are producing? Again, the answer is not quite, right? Of course, literally we cannot shrink ourselves to that size and preserve the properties that we have. But even if somehow we could, objects at that scale, the nanoscale, will have very different properties than the corresponding objects at our ordinary scale have, right? So, for example, gold, right? So we have here a ring made of gold. We value it in part because it's very stable, right? And it doesn't interact very much with the environment, so it lasts for a very long time. But a nanoscale, a gold molecule like that would actually be highly interactive, and so it would. So some of the properties of the bulk matter. So when you add enough of things, change, right? Then the corresponding properties at a much smaller scale. So one of the things that we need to be sensitive to when considering science, and of course scientists are sensitive to that, is the scale, right? So depending on the scale you're studying, objects will behave very differently. And so we devise instruments, the scientific community devises instruments in order to be sensitive to the appropriate scalings, right? And how to interact with objects at the appropriate scale and study the properties that they have at that scale, right? So, so the work then, from a philosophical point of view, is to think about how and what kinds of mechanisms are developed within the scientific practice to create those representations, right? The representations about that are scale sensitive and that produce information that are visually significant, knowing full well that some of the objects that are being visually represented are being represented as a result of a number of choices, static, conventional choices sometimes of how they are going to be depicted, because the objects are literally unobservable, right? So we have no ways of actually seeing them. So we create a technology that has to create a kind of an interface between ourselves and those objects. But choices are made in terms of how these objects are going to be represented. In many ways, some of those choices are not very different from choices that we have encountered in the history of art, right? So if you think about what Picasso did, right, when, for example, he was developing analytic cubism, said, well, if you think about a perspectival drawing, right? Drawing in perspective means, in part, there's a certain point of view from which you're going to draw, and that point of view is fixed. You're not going to change it, otherwise you're going to mess up entirely the perspective of the object. That means that we're going to see an object from a certain point of view, and we're going to see both the back and the front of the object at the same time, or the side, both sides at the same time. So there are choices made from the perspective. So Picasso said, well, but why should we adopt that convention? Why not explore multiple perspectives simultaneously? And the result, of course, with analytic cubism is a distinctive visual object, right? A cubist painting that captures fragments of different perspectives of the same object at the same time. Right? That was a choice, right? That was a choice of how to represent the object. That was no longer constrained by perspective. Now, I want to say that there is also a choice when you're trying to create an image of an object that you cannot see. Right? There is always also there a choice about how we're going to represent that, right? Because you have information. Sometimes the information you have is, for example, in the case of a scanning tunneling microscope. So the tip of that microscope is the smallest possible tip with a single atom, right? And you're going to approach that tip with a conducting surface. Once you approach them close enough, according to quantum mechanics, there's going to be a tunneling current that is going to be established between this single atom tip and the surface. Now, here's the idea. That's Rory and Binnick's idea when they created this instrument. What happens if we keep that tunneling current constant and move the tip around, right? So suppose here's the surface, here's the tip of the microscope. So I approach the surface, establish the current, and leave it constant. Then it starts scanning. So as I approach some protuberance or protrusion on the surface, in order for the current to remain constant, the tip has to move up. Then it goes down if there is some value or some other thing, right? So keeping constant that current and moving, scanning the tip on the surface creates information about the topography, right? So of course, Rory and Binnick end up winning the Nobel Prize in physics for this instrument. And in the presentation of the prize, they said The community was very excited. So now we can see atoms, right? Now, of course, that's an exaggeration. And we cannot literally see atoms, not even with that instrument. And it's, in a way, it's even curious that this instrument is even called a microscope, because, in a way, it behaves more like what you would try to figure out the surface of an object with, shutting down your eyes and then touching it systematically and trying to figure out how it looks without ever seeing it. So it's a daring idea. It's a very interesting idea. But it poses a big problem, because now how are we going to represent that information? Right? So that was an issue that Rory and Binnig and their team had to face back in the 1980s when they were developing the technology. So now how do we present this, right? How would this surface look like? So what they did was something quite interesting. Of course, back then, computer technology was sort of in its infancy in comparison with what we have now. So they said, okay, each time they scan, they do a little diagram and they get some information, and they keep adding each of those scans and printing them out and gluing them together to try to imagine what would that thing look like. And that's how eventually they came up with their own convention codes, right? So when the tip goes down, they represent in a dark shade. When it goes up, you represent in a light shade, and you start creating some contrast, right? And that suggests a kind of a way in which now atoms have this kind of round shape as a result. But of course, the tip of the atom, of the microscope, is a single atom. So it's too big to resolve the shape of an atom. So you need something that will be smaller than that, so you can actually properly sort of traverse the surroundings of the atom. So you cannot, so in a way, the images of atoms that a scanning tunneling microscope provides is an artifact. And of course, microscopists would know that, right? And of course, as a good philosopher, I love to bug my colleagues in the chemistry department and in the physics department and ask them, so what is the shape of an atom, right? And of course, sometimes they say, oh, come on, give me a break, right? Don't bug me with that. But when they're in the good mood, they say, well, we just don't know, right? Because we don't have a technology that actually gives us that kind of information, right? So in that sense, saying that we can see atoms with a scanning tunneling microscope, it's obviously an exaggeration. And that doesn't mean that we're not gathering any information about the sample. We got a lot, right? And again, scientists typically will triangulate, just as Palade did early on with the transmission electron microscope and the ultracentrifuge, right? So microscopists studying surfaces will triangulate atomic force microscopes with scanning tunneling microscopes, some transmission microscope. So they'll try to gather information about the same sample and see whether there are common patterns generated by different instruments, right? So now Ian Hacking, which is a terrific philosopher of science, also very sensitive to issues about the role of microscopes and instruments in scientific practice. He's here to say, yeah, that kind of triangulation is a crucial way for us to determine the reality of what we are studying with those microscopes. Because if there is a common structure that seems to be detected using instruments that operate under very different physical assumptions, it would be a miracle. It would be very surprising that that is the same structure. Right? How come that instruments which are built using different physical principles, rely on different physical interactions, generate information about a sample that is uniform, right? Or there's some common pattern. Now, presented in that startling term, this is a form of argument that philosophers call an inference to the best explanation, right? So the best explanation as to why different instruments generate the same information about a sample is because they are actually tracking the relevant properties of that sample. That's the best explanation. So we should infer that it's true, or more likely to be true than not. Now, that inference is actually, although sometimes used, it's actually very controversial. Certainly from an empiricistically minded philosopher such as myself, right? So Bas van Fraassen was a philosopher of science, probably the most important empiricist philosopher of science in the contemporary scene, raised a number of very intriguing objections to this kind of inference, right? One is called the bad lot argument, and it goes like this. So the idea of the inference of the best explanation is if you have a series of explanations, right? So we saw one, right? About instruments that rely on different physical principles end up generating the same structure. Well, why they do that? Well, because they're actually tapping into what that structure is. That's one explanation. Another one, well, just by chance, it just happened, right? Another explanation, you may say, well, there's none, right? It's just a fact of life that maybe even doesn't require an explanation. So those who adopt the inference to the best explanation strategy are going to say, look, among those three options, right, it's just chance, no explanation, and we're tapping into the reality of the object. Choose the one that is the best one. The best accounts for why we are experiencing things in the way we are. And that one is the one that you should prefer and should take to be true or more likely to be true. Fair enough. So the concern is this, and that's the bad lot explanation. Suppose that I have 15 explanations that I'm considering about a given phenomenon. And I more or less organize them in terms of which of them is the best, right? And I choose the one, say, number 15, turns out to be the best one of all this lot. And I inferred that one to be the true, or more likely to be the true one. However, suppose that unbeknownst to me, the true explanation will be the explanation, if I continue in the same series, the explanation 1,034,000. So I'm way off. It's just that I have no idea. I have this little sample of explanations. I inferred the best one, but it's so so far from the truth that actually it's very misleading, right? Now, of course, if I know that the true explanation is among those that I'm considering, then of course inferring the best explanation may actually get you to the true one. But if I already know that the true one is there, well, then it's unclear that I need inference to the best explanation, right? So this is one example, right, of some concern about a kind of inference or an inferential practice in the case of science. So in many ways, what scientific activity is all about on this picture is an activity of ruling out explanations or ruling out bits and pieces of information that would conflict with the presence of the evidence that we have. And so if we do have the evidence in favor of something, if all goes well, we should be able to rule out those things that would undermine it. And I think by and large, a lot of the hard work that scientists do, it's an attempt of doing that. Of course, they don't rule out everything. You cannot rule out everything, right? But some possibilities are going to be so far-fetched, there's so little reason to believe that they will be the case, that the scientists would just say, okay, we can ignore those. Of course, they do it at their peril, right? Sometimes they come back in that way. But if you think about what the example I gave of Palladi a minute ago, what he was doing when he said, well, look, I've noticed these little dots. Well, maybe this is just an artifact of the method of preparation. So he was ruling out, right, possibilities that would undermine that what he had in front of him was an image of a real phenomena. That's what he was trying to do in that case. Sometimes it's not easy to do that process, because sometimes there are theories that are in place that state that certain things are just impossible. And once you've been guided by these theories in order to reason about the phenomena, you're going to interpret what are the possibilities in light of the theory. And sometimes the problem is the theory itself. So here's an example. So back in the late 20s, physicists were running experiments, bombarding atoms, and of course, at that time, atoms were taken to be non-divisible, right? In fact, that's what the word atom means, no divisions. So you cannot split an atom, right? Because, well, atoms are other kinds of things that could be divided. And it was very curious because in bombarding atoms, they were getting results that they couldn't explain, right? And it didn't make sense, the kind of radiation that we're getting, with the accepted theory at the time. So they redid experiments, tried, well, maybe there's some mistake somewhere, right? So maybe there's something we are not doing properly here. And it took about 5 years of trial and error, making up hypotheses to try to account for what the results were generating, for them to eventually agree that what they've done was to split the atom. They've done that 5 years earlier. The theory accepted then, said this is impossible, so they said, well, this cannot happen, so something else must be going on. And it took about 5 years for them to say, you know what, the theory is wrong. We did what was considered to be impossible. Of course, the sad part of that story is once you split an atom and there's energy released, can that energy be used to split additional atoms and then create a cascade effect? The answer was positive, and from that you think about the idea of an atomic bomb is just a step in the reasoning, right? Of course, and then the hard work is a feat of engineering at that point. But it came out of a phenomena where possibilities were being constrained by certain theories, and theories were saying that certain things could not happen, but they did, and then you have to revise your theories in that case. So, as a philosopher of science, I'm intrigued by those cases, right? I'm intrigued by how much of scientists' reasoning about their evidence is guided by theory, how much is guided by empirical information about the phenomena they're studying, how much is guided by assumptions they may not even be aware of, and they're just bringing into the mix to try to make sense of a very complicated range of phenomena. And of course, there are no easy answers. Science is a complex, fascinating activity. It doesn't have all the answers and never will, because that's the nature of a complex world and our own limitations. But we can always probe further. We can always ask questions and examine the limits of what we can or cannot know, right? Now, along the way, some of the work I'm interested try to bring together areas that sometimes are considered that are better left separate. Right? I mentioned the example of cubism, right? And how thinking about convention codes in pictorial representation in art can help us think carefully about the role of convention codes in setting up representations in science. So I think that kind of interrelation, right, thinking about art, reflecting about science, can be very fruitful. Of course, as long as it's carefully done. Science and art are very different. They each has its own complexities, its own difficulties, its own styles, but they also can, I think we can learn from one another, right? In putting them into contact in the proper way, right? Because I think there's hardly any more sophisticated reflection about images than the history of art. And you have a canon of centuries of reflection about colors, perspectives, conventions, capturing the visual world, capturing what cannot be seen, right? But it's there nonetheless, right? Think about what Rembrandt did with a series of portraits. And he captured almost his inner self, and you can see it in his eyes in some of those paintings. So all the reflection that goes into producing those images, I think, can be very usefully invoked to think about scientific image, and vice versa. Right? So I think there are interesting connections. In some of the work I do, try to explore them, right? Hopefully, making science more humane and more human, because of course that's what it is. It's made by humans, made by people like us, right? And with their own curiosities, their limitations, their determinations, their choices, but also showing that art also has an important cognitive role, right? That we can learn significant things by reflecting about fictional objects, right, in art. I'll give sort of a different kind of example, right? So Dostoevsky once, when he was writing what is sort of a very strange little novel, right, The Gambler. It's a marvelous novel in many ways, very different from all his other novels. In part, I think, because of the way in which it was written. He had a deadline. He had to produce a manuscript of a certain size by a given date. If he didn't do that, he would basically give all the rights to the rights of his publishing future work to a publisher. So he was literally gambling his way around a novel, and he needed to make sure he got this done. He wrote a novel about the behavior of compulsive gamblers, and it's a remarkable novel in that, by reading it, you get a sense of what it's like to be inside the mind of a compulsive gambler. Someone who will gamble everything away, including any money to go back home. And I want to say the following. Of course, he's describing characters that do not exist. Right? And all of those are fictional objects. Right? But he captures something about the psychology of compulsive gambler, that it's just right. Now, I would even say that even if, suppose, there are no gambling in the world, right? Suppose we never developed that concept, right? So they never did any gambling, right? So suppose that we didn't even know why would anyone do that, right? And suppose in that world, it's a world in which Dostoevsky write The Gambler. I would say that what that novel does is to describe what is it like to be a compulsive gambler. So the novel captures something about that fictional object, but also the possibilities involved. We learn something about what's like being a compulsive gambler by reading the novel. In ways that, even if we're not compulsive gamblers, we can appreciate it, can understand what impulse drives that activity. Now, you may want to say, well, look, the novel is realistic because it's ultimately based on actual gamblers, right? So it's just describing the activity of these people, and I think that misses the point of the novel, right? Even if the novel does that, what it does is something more ambitious, right? It tries to capture something about what's possible, right? And we gather information about what's possible by reading that novel. And so it's that exercise on imagination as we read the novel that enhances our understanding of what it would be like to be a compulsive gambler, even if there were none in the world as we live it. Right? So that's of course one example of a cognitive content that art provides us with. I think similarly with what science does, because often there are many areas of science, complex areas of science, in which it's very hard to know exactly what's going on. Right? A famous case is, if you think about the foundations of quantum mechanics, it's very difficult to know, okay, we have this incredible theory, incredible instruments that let us control, say, lasers in ways that are unprecedented. Right? The theory is probably the best tested theory ever built. So the little, say, laser player that you may have at home is built out of results from quantum mechanics. So we control the phenomena, but what's really going on beyond the appearances? Well, for that, there's actually huge controversy. And there are many very different interpretations of quantum mechanics trying to answer that question. All of them are more or less compatible with what quantum theory says, but each of them provides a different answer as to what's really going on. I would like to say that something that von Frassen, I think, quite rightly says. Each of these interpretations tell us a way the world could be if the theory were true. Right? Each of them give us some understanding about the world, about the possibilities of the way that the world could be. In that sense, thinking about interpretations of quantum mechanics need not be very different from thinking about an interpretation of a literary work, such as The Gambler. Right? The analogy is the following. Right? Both tell us something about what's possible. Both give us understanding about these possibilities. Of course, each will do it in their own style, in their own way. Right? So it will be very unfortunate to try to understand the psychology of human gamblers using Schrödinger's equation. It would be very bizarre. Just as it would be very bizarre to try to understand the behavior of atoms using a description in a novel. Right, so that would be those would be category mistakes. However, in their own domain, right, in thinking about possibilities of compulsive gambling and what is involved in their psychology, the novel gives us a very clear picture of what's possible. Just as thinking about the interpretations of quantum mechanics, we get in each one of the many interpretations, we get a picture of what's possible if the theory were true. And I think that kind of modal knowledge, right, that it's the technical term, right, modal is knowledge of what's possible or necessary. I think it's one crucial feature that science provides us, but art also, right? So they have this commonality when you're dealing with extremely complicated phenomena, right? Either the frontiers of quantum mechanics or in the psychology of human gambling. Both science and art are touching the realms of what's possible. And I think that kind of knowledge is important. It gives us understanding. And it's better, and I think in part this understanding is even enhanced by having a plurality of different possible answers. And we may not be able to tell which of them is the right one, but each of one of them allows us to understand better, things that may be involved. And I think that's important, right? So once a philosopher called David Lewis said that the serious business of science is not in knowledge, right, in the production of knowledge, but it's on the elimination of possibilities. And I think he was right? It's, of course, not only the elimination, but also in the creation of possibilities and the exploration of possibilities, that both science and art have something quite common, right? And in reflecting about scientific images, we have an opportunity to bring these two things together, and to bring the knowledge we can gather of reflecting about possibilities when you think about a painting and when you think about a micrograph, and what kinds of possibilities are depicted in each case, and what kind of world each of these objects, cubist painting and a micrograph, what kind of world do they represent and how they represent? Those are questions that I think intrigue us as humans, right? We are very curious about the world around us, but also we're curious about ways things could have been. And it's that kind of thirst for possibilities that drives a philosopher to think carefully about scientific imaging, about pictorial representations in art, and think about how they are interacted and how they're brought together. So some of my work explores that.
I guess I'm interested for what you say in the question of when an image is compelling. I mean, to bring another philosopher into the conversation, Quine basically says you can't eliminate if you think you can eliminate. You're kidding yourself. Just fool around with conditions at the boundary, and you can make any account work for any phenomenon, And if that's right, or even close to right, then what we document with science is partly what compels us of what's out there that we could make sense of if we wanted to. I mean, it's a matter of focusing the dang microscope, At a certain point we say it's in focus. There are other points where we have images that we could do something with, but they aren't in focus. My favorite example, and the one that I really would like to ask you about, is the slow motion video of maggots devouring, I think, a moose. And I mean, it looks like just a mass of maggots if you look at it in normal time. But if you then do 6 hours and speed that up to a minute, it becomes quite an elegant dance, and you see that the thing makes enormous kind of visual sense. It's a compelling image of a sort of spiral as the thing disappears. I mean, the simpler example is you take a hummingbird, you can't see anything, and then, and of course, you slow it down, and you slow it down. You could stop anywhere, but you stop when you see those wings going up and down. And you say, now I've got it. I've got the compelling image. And you look at that, you get that mass of maggots, and at a certain point, it begins to look like a spiral or a dance, and you say, I've got it. So, I'm wondering if you could speak a little bit to this sense that everybody has when they do stop back. Or for instance, you know, you're talking to a mass murderer, and he's going along speaking naturally about his mass murders and what he's done, and seems a little bit like a disoriented librarian. But you can slice that to 1/10 of a second, and get a face that looks very much like a terrifying human being. And you say, now I've got it.
Right.
Now I know what's there. But I'm curious, in all of these cases where we say with an image, okay, now I've got it. Now it's in focus. What do you make of that impulse? As a good empiricist who has to say, but I mean, if you're a really good empiricist, you have to say, well, you can make some sense of any image. You know.
Well, that's a terrific question, and I'm glad you raised it, because it is, first, of course, Quine was an empiricist, but Quine had a lot of other things going on as well, right? And the kind of radical holism that he embraced, that you just referred to. Look, if you make enough adjustments elsewhere in the system, you can always choose to hold certain things with a certain truth value, right? I don't think that that's right as a description of science. I think there are significant constraints, and if you were more of an empiricist than Quine was, you would realize that things won't go that way. Because what will happen is, often what's difficult is to come up with one proper account, right? Rather than, oh, you have tons of them, all of them are just as good as the other, and we cannot choose one over the other, right? So, so I'm certainly not sympathetic with the kind of unrestricted holism that at least Quine in the 50s, in the True Dogmas of Empiricism, for example, seem to be embracing, and in part because of the instruments, in part because the kind of access we have to the world mediated by certain instruments grounds and constrains significantly these kinds of maneuvers, right? Now, grounds and constraint don't uniquely single out. So the other side of your question was, but wait a minute, if you have a motion picture and you change the speed, you can see things that you couldn't otherwise, and that's exactly right, right? And that's in part why these images were so important. Because we can literally see things with a camera that we couldn't otherwise. That only works because cameras are transparent. They produce information that, had the scene before the camera been different, then the image would have been correspondingly different. Had the scene been the same, then the image would have been the same. Right? So, and if you break this dependence between the scene in front of the camera and the corresponding image, you break the transparency. So there are instruments, scientific instruments, that it's unclear that they preserve that transparency. And if they are imaging instruments, then we have serious concerns about those instruments. But as long as they are capturing that, as long as these dependencies in place, we have an epistemological status for the images that are being produced. That is, the images seem to be displaying the phenomena in front of the camera, or under the microscope, or whatever the instrument it is. Now, you said, but wait a minute, we can choose, right? When do I know that I got it, right? Isn't that a human choice, right? Aren't we naturally inclined to choose certain elements over others, right? So why hold the hummingbird exactly at the speed where we can see the wings moving, right? Why consider that moment as the one that is salient, right? And I think that's a difficult and important question. Because of course there is something that is salient for us, given the kinds of creatures we are. I started by saying we are visual creatures, right? But then what that means is we're sensitive to certain visually salient components. But sometimes these components may, again, be just artifacts of our eyes and the ways that our eyes behave. Of course, we are all prone for all kinds of illusions, right? So, well-known kind of Müller-Leyers lines, right? You have, familiar case, you have two parallel lines. They have exactly the same length, but you put arrows pointing in opposite directions. And on the top and on the bottom, right? So, and it doesn't matter how often you look, you measure the lines, the length of those lines, you convince yourself they have exactly the same length, they just don't look that way, right? No matter what, right? Of course, that's just a feature of the way our eyes operate. So it's an illusion. And in part, so when we're dealing with images, we need to be very careful. We're very careful not to let some illusion components creep in, right? Or some choices that we make given the kinds of creatures we are. Of course, we can never eliminate all of those, and maybe we shouldn't, right? And that's why we triangulate. Right? We try to gather additional information. Right? Now, in some cases, the choice of a certain pattern may be relevant. Right? So, for example, why did Rorin and Binnick choose to represent in darkness the point where the tip went down, and in lightness the point in which it went up? Right? That's a conventional choice. Right? But they're bringing in something there about their own choices. The question is whether in making those choices you are somehow biasing the information. If you are, that's a problem, right? And the idea would be you try to avoid these biases by trying to multiply the possibilities of alternative descriptions and evaluate them, right? And so you can determine whether there is something that makes coherent sense. Of course, there is always going to be an element of judgment. That's inevitable, right? But as long as the elements are under control, right? As long as you're testing the bias and trying to diminish as much as you can, well, you may be launching into something significant. And it's not easy how to do it, but the attempts at doing it is exactly what makes the scientific enterprise so fascinating and interesting.
Thank you.